In July 2026, Moonshot AI released Kimi K3, pushing the open weight model class past the 3 trillion parameter threshold. The model architecture comprises 2.8 trillion total parameters, structured as a mixture of expert system. While it contains 896 specialist experts, the routing logic only activates 16 of them per token during inference. This selective activation means that only 104 billion parameters are active during any single forward pass, significantly increasing scaling efficiency. Although the active parameter count is optimized, hosting Kimi K3 still requires infrastructure capable of holding the entire 2.8 trillion weight footprint in memory. Loading a model of this scale requires a specific instance type, the ml.p6-b300.48xl-arch. This server node is equipped with 8 NVIDIA B300 Blackwell Ultra GPUs, which provide the high-density compute necessary for frontier-level models. The GPUs are linked by high-bandwidth interconnects, allowing them to function as a single unified memory pool for tensor parallel inference. To fit the 2.8 trillion parameters onto these GPUs, the weights are distributed in microscaling floating-point 4-bit format, or MXFP4. MXFP4 provides the necessary memory efficiency to fit the model's massive footprint into VRAM without degrading the output quality. Effective deployment depends on using MXFP4 to stay within VRAM capacity limits, while the high-bandwidth interconnects manage the rapid data transfer required across the GPU pool. Because Blackwell GPU capacity is highly contested, instances are rarely available through the standard on-demand pool. This architectural flowchart shows the 2 distinct deployment paths on AWS, SageMaker HyperPod and standalone Amazon EKS. For the SageMaker HyperPod path, capacity is secured through a flexible training plan. These plans provide a committed reservation, ensuring the P6-B300 instances are available without the risk of being preempted. For standalone EKS workloads, capacity is reserved using EC2 capacity blocks. Capacity blocks provide guaranteed access for a specific time window, avoiding long-term contract commitments. Securing this dedicated compute upfront is the only way to prevent scheduling failures once the deployment pipeline begins. Setup for the HyperPod cluster begins in the SageMaker console, selecting Orchestrated by Amazon EKS. Within the instance group settings, you must specify the ml.p6-b300.48x-large as the worker node type. You then link the cluster to your flexible training plan, which assigns the reserved capacity to your specific worker group. The primary management tool for this path is the SageMaker inference operator. The operator is installed automatically if you choose the default Helm charts during cluster creation. It manages the container orchestration, handles weight loading, and maintains automated health checks. By using HyperPod, you minimize manual cluster maintenance in favor of a more automated and resilient serving environment. The inference operator uses an inference endpoint config manifest to define how the model should be launched. The configuration requires the vLLM-OpenAI-KIMI-K3 inference container, which includes day 0 support for the model architecture. The operator uses the model source config manifest to automatically pull the weights from Hugging Face and distribute them across the cluster. Inside the arg section, we set the load format to fast safety tensors to decrease the time required for the initial model load. Setting a tensor parallel size of 8 ensures the model layers are distributed across all 8 B300 GPUs within the instance. The Mo backend auto flag tells the serving engine to manage the routing between the 896 experts, activating only the required experts for each token. Performance is further tuned by enabling the latent Mo tail fusion environment variable, which optimizes the kernel execution for Kimi K3. These specific vLLM parameters are what allow the raw Blackwell compute to function as a coherent mixture of experts endpoint. Teams that require direct control over their Kubernetes configuration can choose the standalone Amazon EKS path. This deployment relies on the AI on EKS project, which provides open-source recipes for inference-ready clusters. Step 1 involves using Terraform to provision the VPC, IAM roles, and the managed node groups that will host the GPUs. Once the EC2 capacity blocks are active, those Blackwell nodes are joined to the EKS cluster as standard worker nodes. You must manually install the NVIDIA device plugin and GPU drivers to allow Kubernetes to schedule workloads on the Blackwell hardware. The vLLM server is then deployed via Helm using the same tensor parallel and MOE arguments used in the HyperPod configuration. In this environment, you can choose to sync model weights from an S3 bucket to the local nodes, which is often faster than downloading from external repositories. While standalone EKS involves more operational overhead, it provides teams with direct control over the Kubernetes networking and storage layers. Both deployment paths result in an OpenAI-compatible chat completions API, exposed on port 8000. This Python example shows how to invoke the endpoint using the standard OpenAI SDK by simply pointing the base URL to your cluster's local IP. The endpoint supports Kimi K3's specialized features, including its complex reasoning mode and structured data outputs. It also handles native tool calling and the model's thinking mode, necessary for agentic workflows. The complex orchestration and hardware routing are now entirely abstract, allowing the application to interact with a 2.8 trillion parameter model through a standard API. Because P6-B300 instances accrue costs quickly, you must delete these resources as soon as they are no longer required. On HyperPod, delete the endpoint configuration using kubectl, and then delete the entire cluster through the SageMaker console. For EKS deployments, you must delete the vLLM deployment, run Terraform destroy on the cluster, and explicitly release the capacity block reservation. Remember that flexible training plans must also be canceled or released to stop ongoing billing. Properly managing the lifecycle of frontier AI infrastructure ensures that deployment remains cost-effective for the enterprise.